it's called Indirect Association. And so just because the midterm is so early this year, we're really covering a lot of this material relatively quickly. But again, be patient. We'll have some examples and review of these concepts starting like on Tuesday. Okay, so now indirect association is actually another concept, which is so far we've been only talking about collecting one variant at a time. Okay, but obviously we're going to, if you think of which variants affect disease, we have a lot of variants, and we're going to be obviously collecting more than one because we don't know which one is it that affects disease. Okay, so indirect association actually has to do with, wow, that looks really weird, and I don't understand why it looks that way because it doesn't look that way on my computer. But anyways, this is the genome. These are the SNPs, right? And what we're interested in is, what if we're collecting more than one variant? Okay, we're going to talk about that in the next couple classes. But also, we're only collecting a subset of the variants, okay, and they're correlated with each other. So, for example, these arrows mean that the value at this variant is going to be similar to this one. So, for example, these might be G's, either G or A. Whenever you have a G, you see an A, and then this is A or T. Whenever you have a A, you see a T there. So like they actually have very similar values. Okay, that's the idea behind correlation. In genetics, for some reason, historical reasons, people call correlation something called linkage disequilibrium. Okay, but whenever you see that, it just means correlation. Okay, so the question is, what's the power of a study with multiple correlated SNPs? And then also, and we're today, right now, going to look at a very specific problem, which is that let's say you're collecting a variant, okay? You're collecting a variant that actually has no effect on the disease at all, but it's correlated with a variant that does affect the disease. This is what we mean by indirect association, okay? And the reason why this is important, actually, this is a critical concept because we have about 10 million variants in our that are different from like the human genome, each of us. The studies that found like all these variants involved in disease, they only collected either 500,000 or 1 million. So they collected either 10% or 20%, sorry, 10% or 5% of these variants. But they were still able to find all the variants that are involved in disease. And the reason is because the way that they picked those 500,000 is that they picked them in such a way that either, you know, they kind of are, the variants, every variant that they didn't pick is correlated with one that they did pick. Okay? Does that make sense? That's the idea. Right? So, and we'll get to all the different aspects of that in the next, I think, 3 classes. But the idea is that, but the question is that now we just computed the power for a variant, assuming that we collected it. So now we're going to say, well, what if we didn't collect it, but we only collected something that's correlated with it? What's the power going to be then? Okay, and that's a very, and this is the concept that actually enabled the how does the correlation affect power? We'll also, in the next couple lectures, we'll deal with the fact that, you know, when we're collecting more than one variant, how does that affect the significance threshold? That's called multiple testing. And then we'll also talk about how do you pick the variants that you're collecting. That's called tags and selection. So we'll talk about all these concepts. But right now, we're only going to say, how does correlation affect the power? Okay. And so now let's assume that we have 2 SNPs, A and B. Let's assume that B is the causal mutation that affects the disease, but we're observing SNP A, okay? So if we observe SNP B directly, our statistic would be, this would be the non-stratified for SNP B, okay? And our statistic would be this come from this distribution. And so then we can compute power and all these things just like we did earlier in the class. Okay, that's fine. We know how to do this. We know how to compute. We can we can measure the significance, we can compute the power, etc. So now what I'm saying is that instead we're observing A. We're observing SNP A. So SNP A is also going to have some kind of a non-centrality parameter like this, right? So the question is, what's the relation between these two statistics if the two SNPs are correlated? Okay, more specifically, right, is that if the two SNPs are correlated, what's the relation going to be between this non-centrality parameter and this non-centrality parameter? Okay, because that's going to tell us how is the power going to change. Okay, so again, like I mentioned a bunch of times, this is a complicated concept. Okay, and I'm throwing them all at you today. Okay, most of what we're going to be doing in the next two classes next week are going to be kind of other layers of this and a lot of reviewing. Okay, so, but that's the question. So what's the relation between these two statistics? So first of all, you need to have some kind of assumptions, and what we're assuming is that essentially that in the case of controls, case of control samples, the correlations between the SNPs are the same. That's what we're basically assuming, okay? And on the slide is a more formal assumption, which isn't so important, okay? But basically what we're assuming is that that if the two SNPs are correlated, that in the case of controls are the same, and that actually does happen. That actually does happen if like in some cases, okay? But we're assuming that the correlation patterns means that if B is the causal SNP, then the conditional probability of A given B, and in the cases, is going to be the same as the conditional probability of A given B in the controls. And so I'm just going to denote that as the probability of A given B. Okay, that's what I'm just assuming. So I'm just assuming that the correlation patterns are the same. Okay, so now if that's the case, we want to relate lambda A, which is the statistic at A, which is what we're observing, okay, with the statistic at B had we actually measured the causal variant, which we're not measuring. So again, B is what's actually causing the disease, so there's some lambda B. We're measuring A, which is just A and B are correlated, okay, and we want to know what is the non-centrality parameter of A, so we can say if I collected A, what would be my power? Okay, because we already know how to, from the non-centrality parameter, compute the power. Okay, that's what we're trying to do here. Okay, so this is the so let's so we want to relate these two values. Okay, how can I relate these two values? So basically these two values. So first of all, what is P plus A? What did I do here? Yeah, exactly. So it's basically, there's two ways that somebody can have, in the cases, have SNP A. The person can either have A and B, right? Or A and not B, right? Those are the two ways. And so these are the, so you can, this probability can be split into these two probabilities, right? These are obviously disjoint groups, right? So then what did I do here? P plus AB, this is the conditional probability formula, okay? And why do I not have a plus here? Because I assume that they're the same in the cases and the controls, basically, right? And then what is this here? This is also the conditional probability formula, right? Because what's the probability of not B? It's 1 minus PB, right? So then what do I do here? What is this one? This is for the controls. Same thing. What is this? This is the difference between these two. And then what did I do? I just factored out this guy, because it'd be times this difference, minus this guy times this difference, right? And then what did I do between these two? I just factored out these two, right? Okay, so now let's look at this formula. So this is actually true. So this is the frequency in the difference in the frequency between the cases and controls for SNP B, right? So if the SNPs are perfectly correlated, meaning that whenever you see SNP B, you see SNP A, what would these conditional probabilities be? What is this one? 1, and what is this one? 0. So what's this difference? 1, right? So that makes sense. So whenever you see SNP A, SNP B, this difference is going to be the same as this difference. That makes sense, right? Okay. What about the following case? What if the probability of, if you have B, the probability of A is 0.4, and if you don't have B, the probability of A is also 0.4, then what happens? What's this difference? 0, right? And so then it doesn't matter what this difference is, this is always going to be 0, right? So if that's the case, that means that they're completely not correlated, right? So you can think of this as kind of measuring what? The correlation, something about how correlated they are, right? Okay, so I have this value. So this here gives me this expression for this difference as a function of this difference times this, right? So now if I want to relate, what is lambda A? I want to relate lambda A in terms of lambda B, because that's going to be the non-centrality parameter at SNP A. This is going to be the non-centrality parameter at SNP B, right? So this is the formula for non-centrality at SNP A. So what if I just plug in this guy down here for this up here? What do I get? This, right? Okay, so then what do I do? What am I doing here? What do I want to get to? I want to get to something that looks like this guy here, because this is the right. So what do I do here? Here, this is I want something like this, but I don't want this one. I want A's, B's down here, right? So I basically multiply and divide by this, right? Okay. Then what did I do? What did I do here? This one I just rearranged all the terms, right? So I end up with these guys here, and these are all the kind of leftovers, okay? And so what is this? This is lambda B. So what does this tell me? This tells me that if two SNPs are correlated, okay, and the non-centrality parameter, okay, at the one that's not the causal one, right, is going to be the non-centrality of the causal one times this kind of a factor here. Can you imagine? This is probably always going to be less than or it's going to be, absolute value less than or equal to 1, right? Okay, well, we'll see that in a second, right? Okay, so does that make sense? We'll see. I'll show an example. So let's just look at this. What is exactly this? And then I'll show some examples that I think will make things a lot clearer. Okay? So here's actually, so if I take this guy here, if I do just some, what did I do here? What rule did I use here? The conditional probability, okay. And then what did I do here? Do you guys remember? I don't know what rule this is called. What is this rule called? Like fraction rule? I don't know. The fraction rule. So I know you probably haven't done this in a while, right? Like this is from middle school. Least common divisor, right? Is that what it is? Like greatest common divisor, something like that, right? So then you get this thing, right? And then look at this numerator. This is PAB. What is these two? What are these two? I can kind of factor out the PBs, right? And what is this? This is PAB, and then if I take this minus and turn this to a plus. PA not B, what is that? That's going to be PA, right? So it's kind of the reverse of the total law of total probability. And so that's how I get this thing up here, okay? What about this denominator? What is this? This is divided by PB, 1 minus PB. Here's the square root of it, right? So if I put the square root into it, I'll take out, this is kind of the square root of this squared, right? So I get this canceled, and so I get something that looks like this. Has anyone seen this formula? I'll give you a hint. It was in lecture 1 in the notes. This is basically R, okay? The formula for R, okay? And so you can write this as R or square root of R squared. I'm only writing it square root of R squared because people oftentimes talk about this as R squared, and so that's what it is, okay? So what does that tell you? That tells you that this is the formula. So lambda A is going to be equal to lambda B times basically R, okay? So what is that? So what if they're perfectly correlated? What will R be? 1. And so these two values will be exactly the same, meaning that the association of one will be the same as the other. What if R is 0? Then what will lambda A be? 0. Okay. What if R squared is 0.8? It'll be 0.8 of, or R is 0.8. It'll be 0.8 of this guy. Okay. So okay. So this is a okay. So this is like one of the things that comes out of this, and we'll actually go over this in the next class as well, which is how many individuals, NA, do we collect at marker A to achieve the same power as if we collected NB individuals at marker B. Okay, so this is so it turns out that it's actually, so in order to have the same power, these two non-trivial parameters would be the same. This is what you can get. If you use the rule, you get something like this. If you solve for NA, you get NB over R squared. Okay? So this is like kind of this specific thing. So this is, okay, so this is a little tricky. So this is actually a way to visualize what's going on. So here we have 3 distributions. We have, this is, let's say, the red and the blue. Think of that as the original power example. Okay? So if you're collecting an actual SNP that you're observing, what do you get? It would be, the power is the area of the red curve beyond the threshold. Okay? So now what I'm saying is that you're collecting a SNP that's correlated with it. So that's going to be like the green curve. The non-centrality parameter is going to be R times the non-centrality parameter of the red curve. So the power is going to be the area of this green curve that's going to be beyond the threshold. Okay, so okay, so let me just get. So is there any questions on this? And I don't know if I should ask questions now or go through the example and ask questions. What do you guys think? You guys, a sea of confusion. Yeah. Okay, biologically lambda, you can think of that lambda A, or lambda whatever, is the strength of the effect of the association that's normalized so it falls onto the normal distribution. Okay? And that's a great question. So then that's what, so like lambda B is the strength of the association for the causal variant, okay? For the variant that's affecting disease. Lambda A is then the strength of the association for the variant that we're actually collecting, which is not really the causal variant, but it's something that's correlated with it. And obviously it's going to be lower because it's not really what we're collecting, okay? And this tells you, this is a way that tells you exactly what is that effect, okay? So this is, again, hard concept, counterintuitive, and a lot of new material. So we'll go over, next week will be a lot of review on this, making this clear, okay? So this green guy here, right, is going to be basically the mean of the so the power is going to, you see how so what happens with the power? If as R goes to, as R decreases, what happens in this curve? The green guy moves farther away from the red. And then less of the green area is above the threshold, so the power goes down. So the less correlated you are to the variant that's actually causing disease, the lower your power is, right? Once your correlation is 0, then you have basically no power. That makes sense, right? What happens is the correlation gets really high. As you go to 1, what happens to the correlation? Yeah, so Z, this one becomes the same as the power of the red. So the green and the red are the same, okay? So now think of it this way, right? Look, if we think of it this way, what are all the different ways that affect the power? There's 3 things that affect the power here. There's lambda b, which is the strength of the variant. There's square root of n, which is the number of individuals that we have. And then there's the correlation. So these are all interrelated, okay? So now, if I go back to this guy, what it's saying is that how many individuals NA do we need to collect at marker A to achieve the same powers of the collected NB individuals of marker B? So if this is the scenario, okay, I'm saying is that, let's say this is how many I'm collecting, okay? What I'm saying is that, let's say if I wanted exactly this power, how many more individuals would I need to collect for A so that this guy would be all the way over here, okay? So you can say that, well, as I increase A, I would move up, 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 up. When do I get to my original point? Okay, well, it turns out that this is the formula. It's just going to be NA equals NB over R squared. Okay, so now does it make sense what this is, right? But just think of it in this curve, okay? So now let's do an example, okay? This will, I think, really make things similar. So there's a collected, okay, so assume that the true, okay, this is actually another, assume the causal SNP is A. I switched it here by accident. And the R squared is 0.8. We collected 400 cases, 400 control individuals. We are collecting SNP B. Actually, okay, so this is at the true SNP, okay? And this is what lambda A is. Okay, we already computed that, 4.02, right? And then what is going to be SB? It's going to be this guy. So the non-sterile parameter at SB is going to be 3.56. Okay, so the power went down, okay? And the power went down from what it was before, okay? 3.56 compared to whatever, the 4.71, okay? Okay, yeah. Oh, that was not good. Okay, so I guess if I went off the edge of the slides, so I have to go there. Okay, well, we have 3 minutes left. So last question, any questions about this? We'll do more review on Friday, 12 to 2, there'll be review of the TA, go over some of the homework and things like that. On a week from Friday, I'll be doing the midterm review in the discussion from 12 to 2, okay? Okay,